Alright, what's up guys? In this video we're going to pick up some calculus here. We're going to do another integration practice video. So I'm going to evaluate the integral x cubed over the square root of 1 plus x squared dx. So I'll probably use a trig substitution for this. And this is going to be a tangent substitution because if you look at what we have the square root of a squared plus x squared. And we know if we have that x is going to be equal to a tangent theta. So in our case, for our trig substitution, what we'll end up having is x is equal to tangent theta. We'll now need to get the derivative, so dx will be secant squared theta d theta when we take the derivative of tangent theta. And so then we just go to our integral and we'll start substituting in. This would be tangent cubed theta all over the square root of 1 plus tangent squared theta, and then this would be multiplied by secant squared theta, and then d theta. And if we simplify under our square root here, I guess I'll write it out for you. We'll have 1 plus tangent squared theta. Well, if we use a trig identity, more specifically the Pythagorean identities, I can write this as the square root of secant squared theta, which is just going to be absolute value secant theta, which we can drop absolute value bars, giving us just secant theta. So what we end up with the simplification is tangent cubed theta all over secant theta multiplied by secant squared theta. As you can see, one of the secant thetas will cancel out, and so what we'll end up with is the integral tangent cubed theta multiplied by secant theta d theta. Now this is the integral we need to deal with now. I would probably rewrite this integral a little bit. I'll rewrite this integral as the integral, I'll write it secant squared theta minus 1 multiplied by secant theta multiplied by tangent theta. Now, how did I get that? Well, the first thing that I did was I simply rewrote tangent theta or tangent cubed theta as tangent squared theta times tangent theta. Remember, I can use a trig identity for tangent squared theta. I can use a Pythagorean identity. And if I use an identity for that, that'll be secant squared theta minus 1. But we still have that tangent theta left over. So this is what you have after breaking up the tangent cubed theta. So now we can do a substitution. The substitution I would do here is u is equal to secant theta. And the reason why I would do that is because the derivative of secant theta is secant theta times tangent theta. And since we have that extra tangent theta hanging around out there, it will cancel out the tangent theta. So what we'll have after we do the substitution is the integral of u squared minus 1 integrated with respect to u. And then this will give us u cubed over 3. And it looks like we'll have minus u. And then plus c. We could put the u back in. And if we do that, we'll have secant cubed theta over 3 minus secant theta plus c. Now, we'll need to use SOHCAHTOA because remember, the original substitution was x is equal to tangent theta. If we solve this for tangent theta, then we'll get tangent theta, that's going to be x over 1, and if we solve for theta, then we'll have theta is equal to arctangent or tangent to the negative first of x over 1. Since we have secant theta here, we'll need the trigonometric ratio for that. So remember that secant theta would just be the reciprocal of the cosine, and so secant theta would be hypotenuse over adjacent, and we already know that tangent theta is opposite over adjacent. So in this case, the opposite side would be x, the adjacent side would be 1, and the only thing that we're missing is the hypotenuse. We have the adjacent side, which is 1. And all I'm using is SOHCAHTOA there, kind of doing it in my head. So we can find the other side. We can find the hypotenuse by using Pythagorean theorem, which is a squared plus b squared is equal to c squared. Now, since we already know that tangent theta is opposite over adjacent, which is x over 1, we're just missing c. So when we substitute in, we'll get x squared plus 1 is equal to c squared, or, you know, if you want to turn it around and write it as c squared, is equal to x squared plus 1. I can take the square root of both sides to solve for c. So if I do that, I'll get c is equal to the square root of x squared plus 1. So if I actually want to draw this out using a triangle, again, the triangle isn't required, but if you want to draw it out just to kind of see what it would look like, we know that the opposite side is x, the adjacent side was 1, and now we found the hypotenuse, which was the square root of x squared plus 1. So when we go back, and we were originally looking for secant theta, remember that's the reciprocal of the cosine, which is hypotenuse over adjacent. And so now we have the hypotenuse. So the hypotenuse here is the square root of x squared plus 1. The adjacent side was 1, remember, so this is just going to be the square root of x squared plus 1. If we divide the square root of x squared plus 1 divided by 1, we'll just get the square root of x squared plus 1. And so when we go back to what we had, remember it was secant cubed theta over 3, and then it was minus secant theta plus c. So all we would have to do is just substitute in. So if we did that, we would just end up having the square root of x squared plus 1 cubed all over 3, and this is minus the square root of x squared plus 1 plus c, but I can simplify that, and I can write this as x squared plus 1 raised to the 3 over 2 all over 3 minus the square root of x squared plus 1 plus c, which will be the answer. So your final answer for this integral here, when we use trigonometric substitution, we were initially asked to integrate x cubed over the square root of x squared plus 1. And when we integrate using trig substitution, the answer here is just going to be x squared plus 1 raised to the 3 over 2, all divided by 3, minus the square root of x squared plus 1, and then plus c. That would be your answer. Right, so let me circle that for you, and that's how you solve it, or evaluate it. Alright, so let me know if you have any questions about how I got my answer. Again, these integrals just take a lot of practice, but other than that, they're relatively simple. And that is your answer. Alright guys, I'll see you guys next time. Y'all take care.